Hello. So, got a fun question for Gemini. Can quantum computing be described as analog computing? Of course not, but let's hear what it has to answer.
That's a fascinating question. Describing quantum computing simply as analog computing is an oversimplification, but it captures some important aspects. Here's a breakdown of the comparison. Arguments for similarities, why it seems analog. 1. Continuous states. Unlike classical digital computers that operate strictly on discrete zeros and ones, the fundamental state of a qubit in a quantum computer is described by continuous parameters called probability amplitudes, complex numbers. A single qubit state can be any point on the surface of the Bloch sphere, representing a continuous range of superpositions between 0 and 1. Quantum gates perform continuous operations, like rotations, on these states. This continuous nature of the quantum state evolution is very much like how analog computers use continuous physical quantities, voltage, current, etc. 2. Sensitivity to noise. Both traditional analog computers and current quantum computers, especially in the NISQ noisy intermediate scale quantum era, are highly sensitive to noise and environmental disturbances. Small perturbations can significantly alter the continuous values, voltages in analog, amplitudes in quantum, leading to errors. Digital computers are generally more resilient because they operate on discrete levels. Arguments against why it's more than just analog. 1. Quantum phenomena. Quantum computers rely on uniquely quantum phenomena like entanglement and quantum tunneling, which have no direct counterparts in classical analog computing. Entanglement creates correlations between qubits that are fundamentally different from any classical correlation. 2. Discrete measurement. While the evolution of a quantum state is continuous, the outcome of a standard measurement is discrete. When you measure a qubit, its continuous superposition collapses probabilistically into a definite classical state, either 0 or 1. Classical analog computers typically deal with continuous outputs, though they might be discretized for readout. This inherent probabilistic and discrete nature of quantum measurement is a key difference. 3. Underlying physics. Analog computers operate based on classical physics. Quantum computers operate based on the laws of quantum mechanics. 4. Error correction. Future goal. While current quantum computers are noise sensitive like analog ones,
So, error correction is still a future goal? Okay,
the long-term goal is fault-tolerant quantum computing. This involves quantum error correction, which often involves encoding information in a way that has digital-like aspects, stabilizer codes, etc., to protect against analog noise, even though the underlying physical system is still quantum and continuous. Conclusion. It's more accurate to say that quantum computing has significant analog characteristics due to the continuous nature of quantum states,
Yes.
amplitudes, and operations, gates, and its sensitivity to noise. However, it is not purely analog computing. The reliance on distinct quantum phenomena, like entanglement, and the fundamentally discrete and probabilistic nature of measurement set it apart from classical analog systems. So while the analogy highlights the continuous nature of qubit states before measurement and the susceptibility to noise, calling it simply analog misses crucial quantum aspects and the digital nature of its output upon measurement. It's best described as its own unique computational paradigm, distinct from both classical analog and classical digital computing.
So, there you have it. Quantum computing has significant analog characteristics, but it is not purely analog computing. Not at all. Alright.